As a data scientist, all you really need to understand a linear model is a regression summary and maybe a correlation heat map. But if we present one of these tables to a non-technical audience, we will be met with blank stares. So we are going to explore 8 methods that you can use to explain linear regression to laymen. These include residual plots, correlation heat maps, weight plots, 4 different types of effect plots, and SHAP values. Hi, I'm Connor and welcome to ADO. We'll be explaining a regression model built using the credit risk dataset. It contains 84 features for 1,000 customers based on their transactions and financial position. We want to use these to estimate their credit score. A high score means the customers have a lower credit risk. Specifically, we're going to use these 7 features. They include a customer's debt to income ratio, the ratio of total expenditure in the last 6 months to the last 12 months, the square of this expenditure ratio, and the one-hot encodings of a gambling feature. Originally, this was a categorical feature that had 3 groups: none, low, or a high amount of gambling. So we won't go over any of the code used to train the model or display the plots, but you can find a link to an article with all of this in the description. There's also a link to a full description of all the features in the credit score dataset. Let's take a closer look at one of those features. We can see that as a customer's debt to income ratio increases, their credit score decreases. So if a customer has too much debt relative to their income, they are less likely to be able to repay a loan. Let's see if we can capture this relationship with linear regression. Here, we have the regression summary of a model trained using the 7 features. We can see the model has captured the negative relationship with debt to income. The relationship and the relationships with all the other features is also significant. Really, if you have a statistical background, the summary would provide most of the insight you need when it comes to understanding the model. When it comes to explaining the model, we can do a lot better. The first method is the residual plot. In my opinion, this is the best visualization for understanding the performance of a regression model. It is a scatter plot of the credit score predicted by the model versus a customer's actual credit score. We then add the y equals x line in red. This gives the line of perfect predictions. That is if the model always predicted the actual credit score. In statistics, a residual is the difference between a model's prediction and the actual target variable for that instance. In this plot, we can see the residuals for all the customers. They are given by the distance on the x-axis between a point and the red line. In our case, it would be the difference between the actual and predicted credit score for a customer. If we go back to our regression summary, the residual plot is directly related to the R-squared value. This is a metric used to evaluate the overall fit of the model. It tells us how close the model predictions are to the target variable. This is what the residual plot is visualizing. The more scattered the points around the red line, the lower the R-squared value. The benefit of the residual plot is that instead of a mathematical formula, we present the information in a way that is easy to grasp for a non-technical audience. Okay, so the residual plot tells us if the model is making accurate predictions. What if we want to understand how the model is making those predictions? Well, most of the remaining methods are aimed at explaining how the features are related to the target variable. Before we get to those, it's worth exploring how the features are related to each other. To do this, we can use a correlation heat map of the features. This gives the correlations of the numerical features used in the model. Now, this plot does require some basic statistical knowledge, and you may not even have to present it. Really, it is more useful for a data scientist to use when explaining the relationships between the individual features and the target variable. That is, we want to make sure there are no highly correlated features, also known as multicollinearity. Our model has 2 highly correlated features. This is to be expected as one of the features is the square of the other. In general, a good model should not have multicollinearity. As discussed in a previous video, highly correlated features suggest we have redundant features in the model. They can also make the model harder to explain. Changes in one feature will cause changes in another, and we cannot talk about feature trends in isolation. This weight plot can tell us a bit about how the model is making predictions. For every feature, we plot a point for its weight or coefficient. These are taken directly from the model summary. We also plot error bars using the standard error for those coefficients. For each feature, the weight plot tells us how a 1 unit change in the feature's value will change the predicted credit score. The error bars give us an indication of how certain we are about that trend. The issue with this plot is that the features will all have different scales. For example, we can expect income values to be larger than the ratios. As a result, the coefficient for income will be smaller. So we must not interpret larger values in the weight plot to mean that the feature is more important to a prediction. The effect on credit score will depend on the coefficient and the feature's value. This brings us to the effect plot. An effect is how much a feature has changed a prediction. The coefficient for income is 9.011 times 10 to the power of -5. And if the customer's income value is $50,000, then the effect of income on the predicted credit score for this customer is 4.51. We can similarly calculate the effects for every feature and customer. These are the feature values multiplied by the coefficients. The result will be a matrix with shape 1000 by 8. In other words, for each of the 1000 customers, we have the effect of the 7 model features and 1 constant. These tell us how these features have changed the predicted credit score for that customer. As the feature effects are linear, we can add the effects of some of the related features. This will give us a clearer insight into the effect of the base feature. For example, we will have one effect for gambling instead of the individual effects for the 2-1 hot encodings. We'll also have the overall effect for the expenditure ratio instead of the individual effect for the linear and quadratic term. Finally, the effect plot is a box plot of the 1000 individual effects for each feature. The effect plot shows which features tend to make the largest contributions to the credit score. The value of that effect also tells us the relationship that feature has with the target variable. For example, the debt to income ratio has negative values. So as the ratio increases, we have a smaller credit score. We can make some adjustments to the effect plot to improve its interpretation. In this case, we have excluded the tails of the box plot so that we only display the typical effect range for each feature. We also center the box plot at the linear model's intercept. This can give some context to the effects. For example, before we could say that the debt to income ratio tends to decrease the credit score by 50 points. Now we can say that the feature tends to decrease the credit score from 675 to 625. The mean effect plot is created by calculating the average of the absolute of all the individual effects. This provides similar information to the previous plot. In fact, it provides less information. It ignores the nature of the relationships, and we no longer see the spread of the effect. Yet, it is still useful for focusing on one question: which feature has the most effect? In other words, we can use this plot as a measure of feature importance. The effect and mean effect plots are both used for global explanations. They can tell us how the features contribute to the predicted credit score in general. But what if we have a disgruntled customer demanding a reason for their low credit score? In other words, they want a local explanation. Well, this is where the individual effect plots come in. The individual effect plot is simply an effect plot that is annotated with the effects for one instance. That is the contribution of each feature to the predicted credit score for that customer. For this plot, we have used a red X to mark the effects for the first customer in the dataset. We can use this plot to find the most significant features for a given customer. Why is my credit score so low? Well, a major factor is your debt to income ratio and expenditure behavior. In general, these allow us to contrast a customer against the general population. When answering questions like the one above, it's useful to pair the individual effect plot with plots of the feature distributions. For example, here we have the distribution of the income to debt ratio. We can see that the customer has a relatively large value for this feature. We can now say your debt to income ratio is larger than what we typically see. We are not sure you'll be able to afford any more debt repayments. This is why your credit score is so low. The individual effect plot is also not limited to only one customer. Here we have another customer given by the blue X, along with the original customer given by the red X. This is useful for contrasting two customers. We can answer questions like, why was she given a loan but not me? After considering GDPR, of course. Going back to global explanations, the effect plot is limited in its ability to explain trends between the features and the target variables. To see this, we can plot all the individual effects for a feature's effect versus the feature's value. We can see the effect trend for the income to debt ratio. The slope of this line is equal to -9.256. This is the model coefficient for this feature. We can now understand what the coefficient means in terms of the effect on the predicted credit score. Until now, we have explored model-specific methods. They can only be used for regression models. This is because we have used the model's coefficients to explain how it is making predictions. As a result, you will not be able to use the same methods for models like decision trees, random forests, or neural networks. For these, we must use other model-specific methods, or we can use model-agnostic methods. The latter can be applied to any machine learning model. If you want to learn more about model-agnostic methods, I highly recommend my Explainable AI course. I cover how you can build interpretable models and explain them using PDPs, ice plots, ALEs, Friedman's H statistic, Lime, and the next method in this video, SHAP. Even better, you can get free access if you sign up for my newsletter in the description. This is by far the most useful package for explaining nonlinear models. Yet, it can also be used for linear models. This is useful when you are comparing multiple algorithms. Applying SHAP to all of them will give you a consistent method for interpreting the models. We can display the SHAP values for the first customer using the waterfall plot. The arrows give the contribution of each feature to the predicted credit score. The waterfall plot provides similar information to the individual effect plot. A key difference is the base value. In the effect plot, we use 0 for the intercept of the model. SHAP plots use the average predicted credit score across all the customers. Like with individual effects, we can aggregate SHAP values. For example, here we have the SHAP bar plot. Each bar is calculated by taking the absolute mean SHAP value for each feature across all 1,000 customers. Notice how similar these are to the mean effect plot. Likewise, the SHAP B-swarm plot will be similar to the effect plot, and the SHAP dependence plot is similar to the trend effect plot. If you want to learn more about SHAP, then check out this playlist. And if you're interested in explainable AI, you might enjoy this introduction to the field. Otherwise, remember, you can get free access to my XAI course. I hope to see you there.